Okay. Good afternoon to everyone, and thank you for being here today. And the authors of this work are Giovanni Meneghetti, Alberto Campagnolo, that is also here, and Carlo Dengo from Carraro SPA, that is a leading company in the production of axles and transmission for off-highway vehicles. The aim is the fatigue assessment of tube-to-plate steel welded joints with the weld ends of automotive interest. The welded joints have been fatigue tested by means of an uniaxial fatigue testing machine. Then the real geometry of the welds have been acquired by a 3D scanning technique. Then it has been introduced in a FE model to apply the peak stress method, taking advantage of an automatic application developed at the University of Padua that we will cover much more in detail in the next section by Alberto Visentin. And finally, by applying the peak stress method, we can fatigue assess the welded components. So, why the peak stress method? Because it can be used also with components with complex geometries, so real components, and it's applicable with uniaxial as well as multiaxial stress states. On the right side of the slide, you can see the summary of the theoretical background of the method. So the damage parameter is the average strain energy density, the SED. The SED is a function of the NSIFs, the notch stress intensity factors, that could be rapidly estimated by means of the peak stress method. And then talking about the fatigue assessment, it could be defined in a range of the equivalent peak stress, and the data expressed, the fatigue data expressed in terms of range of the equivalent peak stress will be compared with a design PSM design scatter band chosen on the basis of the local biaxiality ratio lambda. So the PSM design scatter band have been validated on the basis of several geometries taken from the literature, and here you can see the comparison between the PSM design scatter bands for steel welded joints and the experimental data taken from the literature. So the welded joint that we have tested are basically a plate welded to a tube with an intermittent fillet welds, and we obtained two different geometries, transverse geometry and longitudinal geometry, test both in as welded and stress lift condition. Here you have the parameters related to the detail of the junction, useful to define the element size to apply the peak stress method. This is the testing machine that we use. Is an uniaxial machine for fatigue tests, and in this macro there is detail of the local geometry of the weld end and of the weld start, and as you can see, they differs a lot. The number of cycles to technical crack initiation was chosen in correspondence of an increase equal to 0.1 millimeter of the maximum displacement of the actuator of the testing machine. In our fatigue test, we have explored a number of cycles ranging between 50,000 cycles to 2 million cycles. Okay. On the right side, there are the cracks that we have seen in the transverse joints. The transverse joints show cracks both at the weld end and at the weld start. I would like to focus your attention on the crack at the weld start. It is difficult to see with naked eye, and we only saw this crack after performing die penetrant inspection. On the other end, the longitudinal joints show crack initiation at the weld end at the plate side. The data expressed in terms of nominal load force range against number of cycles to crack initiation have been statistically analyzed to identify the inverse slope K and the scatter index. The inverse slope near to 5 for the transverse joint, and is equal to 3.42 for the longitudinal ones. The real geometry of the welds have been acquired by a fringe projection technique This work has been carried out in collaboration with the LIN laboratory of the University of Padua, and I would like to thank you, Professor Francesca Ucchedu and Mattia Maltauro. So a transverse geometry tube-to-plate welded joint have been placed in a rotary table, and several views have been acquired with the 3D scanner. Then those views are combined to obtain the parametric weld surface that is assembled with the nominal model of the plate and tube to end up with the parametric 3D model of the transverse welded joint. To obtain the same parametric model for the longitudinal joint, we have simply rotated the acquired welds of an angle equal to 90 degrees along the axis of the tube. Okay, on the left side, you have the nomenclature that we have used to identify the 4 welds that we have introduced in the FE models. And here is the detail of the mesh of tetra 10 elements of ANSYS workbench with an average element size of 0.4 millimeter to comply with the requirements to apply the peak stress method. And far away from the welds, we have used a mesh with an average element size equal to 2 millimeters. There are 4 lines in which lies the tips of the V notches that are critical lines for the crack initiation, both at the toe side and at the root side. So we have analyzed those 4 lines. Here are presented the distribution of the range of the equivalent peak stress along the welds. On the left side, the data for transverse geometry. As you can see, the maximum value of range of the equivalent peak stress is reached in correspondence of the weld start at the tube side toe. That is an agreement with the experimental data. It was the crack difficult to identify the naked eye that I showed you before. On the other side, the longitudinal geometry shown the highest value of range of the equivalent peak stress in correspondence of the weld end at the plate side tube, again in agreement with the experimental data, but also looking at the data referring to 2 different welds out of 4 that we have acquired and analyzed. You can see there is a scatter of the data in correspondence of the crack initiation point due to the geometrical effect of the real weld, so it's a process effect. The data shown here are related to the as-welded test condition, but you can simply derive the values for the stress relief joint by multiplying the range of the equivalent peak stress for the square root of the CW coefficient. And also the effect of misalignments has been investigated and resulted to be negligible. Here is the comparison between the experimental data expressed in terms of range of the equivalent peak stress and the PSM design scatter band chosen on the basis of the local biaxiality ratio lambda. The experimental data related to longitudinal geometry are in very good agreement with the PSM design scatter band, as you can see here. On the other hand, the experimental data related to transverse geometry joints are on the safe side. In our opinion, this is due to the criterion adopted to identify the number of cycles to crack initiation, because in correspondence of that number of cycles, we had multiple crack initiation and also cracks difficult to identify with naked eye. So, in conclusion, steel welded joints with weld ends have been fatigue tested. The local real geometry of the intermittent fillet welds have been acquired by means of a 3D scanning technique and then introduced in an FE model to apply the peak stress method. Talking about the transverse geometry, the PSM correctly estimates the experimental crack initiation zone, but the experimental data are on the safe side with respect to the PSM design scatter band. Talking about longitudinal geometry, the PSM correctly estimates again the experimental crack initiation zone, 50% of the experimental data is within the PSM desired scatter band, and 50% is on the safe side. Those values are referred to the maximum values, the scatter that I show you in the slide before. So the maximum scatter of the experimental data, the maximum value of the scatter of the experimental data. So that's all to me, and I would like to thank you for your attention.
Thank you.